This is problem 1 on practice exam 8 of chapter 2 in the book Problem Solving with Differential and Integral Calculus. We're going to work with the volume of a cube. So we have the normal equation, V is S cubed, the volume of a cube is the side length cubed, and we have a plot right here. Part A asks us to derive dv dt, which is the slope of the line at any point, using the normal equation. So just take the derivative. Part B, use this expression to get the slope at 10 centimeters. We're just going to plug it in. That's simple. Part C, we're going to draw a tangent line at 10 centimeters and compare it with the result we got from part A. And part D asks us to get the cube root of 1006 using differential calculus. So part A, derive dv dt. So we have the normal equation, V is S cubed. We're going to change S and see how V responds. Change S by ds, V changes by dv. We want to determine dv for any S and ds. So the volume of a cube with side length S plus ds is bigger than the volume of a cube of side length S by an amount dv. So there's our equation. We can cube it out, and we have V right here is S cubed. So we can get rid of those two terms. The difference is what we're after. And there's the difference, and we can throw out the higher order terms and then divide both sides by ds to get the slope. dv ds is 3s squared, and if you have been trained in calculus, you know that the derivative of s cubed is 3s squared ds. So before we move on, before we get to part B, let's see if we can understand what's going on here. We have this difference equation. So this is true for any s. It doesn't have to be small. This is exact. So what are these pieces? What is 3s squared delta s? Why is that there? Why is there a 3? What is 3s delta s squared? And what is delta s cubed? How does that fit in? So let's start by imagining a cube of side length s and then adding pieces to make a cube of side length s plus ds. We're going to build a complete cube of side length s plus delta s. So we'll start with that cube. It's s by s by s. We need 3 flat slabs, one on the front, one on the side, one on the top, and they're going to be s by s, and then they're delta s thick. So here's one, there's another, and there's another. Each one of these slabs has a volume of s squared delta s, right? S delta s thick. And that's where the 3s squared delta s comes from. The first term is the 3 slabs. Now we need 3 rods, 3 square rods to go along the 3 edges. Each of these rods has a volume of s by delta s, right? They're s long, and then delta s by delta s here. So let's put these 3 rods in, and there is the 3s delta s squared. Now we have this little cube in the corner we need, and that cube is delta s by delta s by delta s. It's got a volume of delta s cubed. Let's put that there, and there is a cube with side length s plus delta s, and that's exactly where the difference equation comes from, each of those 3 terms. If the change is infinitesimal, then all you need is the 3 slabs, which is 3s squared delta s. So you can construct a complete cube with no gaps with an infinite number of infinitely thin square slabs. That is, the integral of 3s squared ds is s cubed. Now, if you say, well, there's going to be some gaps in there, well, yeah, you're imagining a finite number of infinitely thin slabs. You need an infinite number, and then there's no gaps. Okay, now we can go to part B. Part B just asks for what's the slope at 10 centimeters. So we can just plug it in, and we get 300 cubic centimeters per centimeter. That's the rate of change of the volume with side length at 10 centimeters. Part C, check with the tangent line. So let's locate the point, draw a good tangent line. There it is. The rise is easy. It looks like 2,500 cubic centimeters. The run, what is that, 6.7? 6.7 to 15 is 8.3 centimeters. So the slope, 2,500 cubic centimeters divided by 8.3 centimeters, which we get 301, which we round to 300 because we're taking a tangent line. And that's what we got with the derivative. 300 centimeters cubed per centimeter at a side length of 10 centimeters. On to part D. So we know that the cubed root of 1,000 is 10, and we know that the cubed root of 1,000.6 is a little bit bigger than 10. And we can use differential calculus to calculate how much, get a really good estimate of how much. So there's the change in volume divided by the change in the side length, and that's 3s squared. The volume that we want to work with is 1,000.6, so that's a dV of 0.6. So first we solve for ds because that's what we want, and we have a license. We understand. We can plug in 0.6 centimeters cubed in for dV. We should call it delta V, but we just plow ahead. And we know it's going to be a little bit off because it's not infinitesimal, but that's okay. So there's our ds. If we want to increase V by 0.6 at 10 centimeters, a side length of 10 centimeters, we have to increase the side length by 0.002 centimeters. So the cubed root of 1,000.6 is 10.002. That's a good estimate. Should be slightly high because we're assuming all of the change is coming from only the three slabs, 3s squared. So let's use a calculator and take the cube root of 1,000.6. And this is what we get, 10.0019998. So this is 10.002 to 7 significant digits, 8 significant digits. A very good estimate. It's not exact. We left off some contributions, but we understand that, so that's okay. It's important to understand what's going on.